Give me one moment. All right, so we're going to finish up on the notes for 6.2, and we're going to do, we did examples 1 through 3, so we'll walk through example 4. We're going to see that things are a little bit different with example 4. Still same setup, same equation, but the order that we're looking for information is going to be a little different. And then after that, we'll move on to Slotefield's notes. All right, so example 4. In a certain culture where the rate of growth of bacteria is proportional to the amount present, the number triples in 3 hours. Okay, so let's look at what this is saying here. Rate of growth of bacteria, we know that we can let B represent bacteria, but we see rate of growth, so we know that this is some sort of a derivative, so we'll say B prime. We see that it is proportional to the amount, so we know that proportional equation is going to be in the form of y equals kx. So we know that k is going to show up here. Everything's in the numerator. To the amount present. So the amount present is the amount of bacteria present. So that's just B. And just like how last Thursday, we saw that these are all kind of the same formula, right? Y prime equals ky, B prime equals kb, R prime equals kr, P prime equals kp. They're all going to result in this general equation. Y equals ce to the kt, but we'll just let B represent our dependent variable. So we say B is equal to ce to the kt. So we're skipping all the calculus process. We did that with example 1, where we separate the variables, dependent on the left, t's on the right, take the antiderivative, and worked our way down to this equation. All right, so just like before, we're going to list out order pairs, time being the independent variable, and then in this case, bacteria being our dependent variable. Okay, we'll let T represent time. We'll let B represent bacteria. Okay, the amount number is going to triple in 3 hours. Let's read the rest of the statement A here. If at the end of 12 hours there were 10 million bacteria, how many were present initially? So we like to start off with something involving 0, right? Just like how before we like to have a starting point and let that starting point be 0. So we know that there is some initial amount. So I know that's going to be times 0, but the problem is that we don't know what that value is. Okay, normally that's the first number that we look at, but in this case, it's going to be the last number that we find because that's the unknown. But in the past, we saw that C basically represented our initial amount, right? Here, example 3, 60 milligrams are present now, right? So our initial amount is what fills in that C value. So I'm going to just let C represent my unknown initial amount, and we'll build up to working backwards to solving for that C. So we know that times 0, we have some initial amount of bacteria, but we don't know what that number is. Right? So we can build off of this, though, because we know that in 3 hours, this initial number is going to triple. So we know that 3 hours later, my bacteria is going to grow to 3 times the amount, so 3 times C. Okay, we're able to build that relationship based off of what I created generally. And one last thing is we can create a third order pair. After 12 hours, there's 10 million bacteria. So 12 hours later, 10 to represent in terms of, yeah, so rather than writing out 10 million, I'll just let 10 represent millions. What that means is at the end, whatever number I get, I'm going to multiply that by a million to bring it back to the actual number. But right now, I'll just let this small number represent millions. Okay. Just like before, we're going to be plugging in order pairs and solving for missing variables. But we know that the 0c is not going to help us out. Right? If I put 0 in for t, it's going to wipe this whole thing out. I'm just left with 1, c equals c. That's not going to bring me anywhere. Right? So we're not going to be able to make much progress here. So let's go to the second order pair. Maybe this can help us out. I'll put 3 in for time, and I'll put 3c in for bacteria. Let's see what happens here. 3c goes in for B. Ce to the k times 3. I get the c's to cancel out. And that's nice because once the c's cancel out, I'm able to solve for k, right? So 3 is equal to e to the 3k. Okay. Take the natural log of both sides. That will allow that k to come down in front. Okay. Once that 3k comes down in front, we get that natural log of e to go away. Okay. Divide both sides by 3. So k is equal to natural log of 3 over 3. We want to leave our k value in exact value form so that we can increase our accuracy at the very end with our approximation. Normally, we would get that equation to update with the c value, but we know that the c is going to be the last number that we find, but we can still update our equation, but now we're going to be updating with the k first. Now that I have my k value updated, let's see what else I can do. What if I use this 1210? All right, again, the 0c is not going to bring me anywhere, but this 1210 can maybe help. If I put 12 in for t and 10 in for b, I can get these numbers, get these variables to be replaced with numbers, and then that will leave me with the only variable standing, and we can solve for c. So we're having to work backwards a little bit, plug in everything except the original order pair, because that's the unknown that we're looking for. So 12 goes in for t, 10 goes in for b. I can do a little bit of cleanup. 12 divided by 3 is 4, but ultimately I'm going to take this number, I'm going to divide it over to the left side, and I can isolate c, and then that's what we're looking for. Our c is going to be our initial amount. Okay, I'm just going to do a little bit of cleanup so I don't have to plug in as big of a as many numbers into the calculator. So I'm going to reduce the 12 over 3 to be 4, divide this over. Okay. 10 over e to the 4 ln 3. If I put this in the calculator, I get 10 over 81. Convert it to a decimal, I get 0.123. So my C, my initial number of bacteria is 0.123, but we do know that this represents a million, right? So we need to multiply this by a million because we started with 10 representing 10 million. So this got to be 0.123 million. So multiply that out, we get 123,000. So this is our approximate number of bacteria initially. Okay, any questions here? We're going to skip B for now, finding the specific equation. We just want to, if we can get to that C value. But really, we're just taking this and dumping it into this equation here. So it's not too bad, right? Just put that in for the C, whatever that mess gives us, that's our specific exponential growth equation. Yeah, if you want to see that. Yeah, putting the K and C value into my B equals CE to the KT. Okay, any questions? All right, let's look at today's notes for slope fields. All right, let me read through the notes and then we can practice creating some of them and also interpreting a completed slope field. So slope field is a graphical approach to look at all the solutions of a differential equation. Slope fields consist of short line segments representing slope or the steepness sketched at many different points. So ultimately our slope field, we're not going to be creating with this many points, but this is what a slope field looks like. So all these slope segments representing the slope at specific points. Okay. These line segments are tangents to a family of solution curves for the differential equation at various points. The tangents show the direction in which the solution curves will follow. Slope fields are useful in sketching solution curves without having to solve a differential equation algebraically. So that's what ultimately is happening here. We've been solving differential equations, right? We'll separate the variables, take the antiderivative, and we're able to solve it algebraically and through calculus. But slope fields allows us to stay at the derivative level, stay at the differential level, and then just sketch out these slope segments, and it will give us a picture of the solution without having to solve it algebraically. So there's two scenarios. One scenario is where we can find the solution, but we just opt to create a visual aspect of it. The other situation is where we're unable to solve a differential equation algebraically. That's not going to happen for us in terms of you're never going to get a problem where you're asked to solve a differential equation and you realize, wait, I can't separate the variables, or there's no antiderivative rule to apply. You know, the problems are curated in a way where there's a definite solution for every problem that is presented to you. But there are many differential equations out there where you can't separate the variables algebraically, or we just don't have rules that matches with our problem, right? Because we see, even though we have all these rules for integrals, they're very limited, right? If it doesn't match exactly with the rule that we have in front of us, then we don't have a rule to use. And there are different rules out there that we're not seeing, but then there are also many problems that we just don't have a way to solve it. And in those situations is where slow fields is really helpful. It can give us a picture of the solution, even if we're not able to solve for it algebraically. Okay, so that's really the benefit of slow fields. It gives us a way for the solution, even if we're unable to solve it. But for our purposes, we're just going to learn about how to interpret a slow field and how to create one in terms of how it's created. So here are the steps. We're going to be identifying order pairs indicated on the graph. So when we're creating slow fields, we're only going to be doing it at just at a few points. Okay, we're not going to get a full picture, but we're just creating it enough to show that we understand how to create it if we were to create the full picture. Next, we're going to plug in the order pairs into the differential equation to find the slope. And then we're going to sketch short line segments representing the slope through that given point. And finally, we're going to repeat this process for all the remaining order pairs. I'm going to skip these two statements and come back to it when we have more knowledge into the second page. So example 1, it says, sketch a slope field for the given differential equation at the indicated 8 points. Now, I want to come back to this this word here, differential equation. I know that we're looking at that and it feels foreign, right? It feels like something new. It feels like something that we haven't been working for a long time on, but we actually have been. We've been dealing with differential equation ever since we started derivatives. Differential equation is basically just another way of saying a derivative formula. Which, for our purposes, since we learned power rule from August or September, was that it's just basically the derivative function. So that's all a differential equation is. It's just a derivative function. So here's an example, right? So from first semester, we learned that if I gave you a function and the function was 2x cubed plus 6x, and I asked you for the derivative, you would just go through and find power rule, right? 2x cubed would become 6x squared, 6x would become 6, and you would know that you can plug in any value into the derivative. In return, you'll get a number, and that number is going to correspond with the steepness of the original graph. Same process here. Okay. It's just that we're calling it a differential equation because our y's are kind of out of place, and it's a lot of times not going to end up being a function. It is not going to end up being something that will pass the vertical line test. So we give it a more generic name. We give it a differential equation, but I just want you guys to think it's the same thing, right? It's the same thing as first semester. It's just that now we're able to learn how to take the antiderivative, but really it's just the same. It acts the same way as f prime from first semester, right? You give it information, in return, it'll give you slope, and that slope describes, that number describes the slope of an original function. Okay, so this is not a new concept. We're just doing things a little differently with it, but it's the same idea as f prime from first semester. Okay, that's all differential equation is. So that's what we're going to do. We're going to identify the order pairs that are highlighted here. We're going to plug our order pair into the function, into the derivative. In return, we'll get a number, and that number will represent the steepness through that point. Okay, so let's list out the order pairs that we see in front of us. Okay, so I'm going to start here. This order pair is at -1, 2. This order pair is at -1, 1. This order pair is at -1, 0. This order pair, -1, -1. order pair here at 1, 2. Order pair 1, 1. 1, 0. And 1, -1. So now we're going to take each of these ordered pairs and put it into the derivative, and then in return we'll get a number, and that number is going to give us the slope segment to put through that point. So if I put -1 in for x, I get -1 minus 4. So that gives me -5. So I'll put -5 in this slot. And what we're going to do is we're going to sketch a slope that resembles -5 to the best of our ability through this point -1, 2. Okay. Accuracy is not that important as long as you're in the ballpark. -5 is a relatively steep slope, so I'm going to make a relatively steep negative slope through that point. Okay. And we'll move on to the next order pair. Put -1. 1 in for x and y, so I get -1 minus 2. -1 minus 2 is -3. So what does -3 look like? -3 is a negative slope that is not as steep as -5, but still a negative slope, still relatively steep. So I'm making it slightly less steep, but really, as long as you have a general idea, that's the accuracy again is not that important. Okay, put -1, 0 in for x and y, so -1 in for x, 0 in for y, I get -1. So I'm going to make my slope negative, but not as steep as this, so 45 degrees here. Okay, moving on, -1, -1, I get -1 plus 2, which is 1. So I'm going to transfer this to a positive slope now, +1. So it's going to be in this direction. And then we're just going to go down the line, repeat the process for all these others. So if I put 1, 2 in, I get 3. Sorry, -3. If I plug 1, 1 in, I get 1 minus 2, which is -1. If I plug 1, 0 in, 1 minus 0 is 1. If I put 1, -1 in, I get 1 plus 2, which is 3. Okay, so 1, 2, we get -3, so I'm going to create a slope that's similar to this one here, not as steep as -5, but more than -1. -1, 1, and 3. Okay, any questions there? Okay, let me list out the order pairs. Oh, sorry, before I move on, there's exceptions that I want to talk about. So I want to put exceptions down here. All these are just non-zeros, right? Any non-zero, we know it's going to be a diagonal slanted line, various degrees of steepness. But let's talk about what happens if we're getting like 0. So if I get slope equals 0, so for instance, if I end up with a dy dx giving me 0, or it could be something like 0/4, which is also 0, right? That represents a real number. What you're going to do is through that indicated highlighted point, you're going to put a horizontal line through it. Okay. Okay. The other exception to these numbers is slope undefined. So slope undefined, we're going to see it in this example actually. If my dy dx gives me something like 3/0, then we consider that as undefined. And what you're going to do is, if it's undefined, through that point, you're going to leave it completely empty. Okay, leave that order pair space empty. Don't put a line segment through it. Now, what a lot of students want to do is I think a lot of us associate undefined slope with a vertical line, but no vertical line. Okay. Just leave it empty. Okay. If you put a vertical line through it, then that's incorrect. Okay. So slope 0 is horizontal line. Slope undefined, leave it empty. So let's see if we can fill this out and create slope segments through those indicated points. So let's put it in this order here so we can match our answers a little quicker. So go ahead and copy these order pairs down and take the time to plug into the appropriate derivative equation. Whatever number you get, you're going to translate that number into some steepness at that point. Okay, so let's spend a minute to try that, and then we can compare our answers. Okay, let's see how we did here. So we should be getting all these values as slope representations, and we'll try our best just to sketch what we think is the slope. Like 1/2 would be a really gradual slope through 1, 2. So I just made it as gradual as I could. But notice that we do have two undefined slots here. So -1, 0 and 1, 0. So that means we're going to leave those order pairs empty. Okay, don't put vertical lines there. Just leave it empty. Okay, any questions? All right, let's go to the second page where we're going to be able to see a more full picture of the slope field, right? So this is a tedious process, right? Having to create all these segments, but it's not too bad if it's only a few points. But you can tell that we're not really getting a full picture, right? We really don't know how the flow of the graph is going to be beyond these points. So what we're going to do is next page, we're going to see a completed filled out slope field, and we're going to see if we can make interpretations on it or match the slope field with the correct equation that goes along with it. Okay, next page. So this is a completed slope field. Okay, we're going to determine the differential equation graphed by each of the slope fields below. Then we're going to sketch a solution that passes the indicated point. Now, my strategy for this to make things faster is we're not going to be looking at each individual point. That would just take too long. At least what we want to do to speed up this process is we want to make general observations and then use the general observations to eliminate the wrong choices. And then once we're down to one or two options, then we can look at more specific ordered pairs if the general observation doesn't help us eliminate. So I think that's going to be the best strategy for the test as well as for the AP exam. If you see on the AP exam, you always want to try to eliminate the wrong choices quickly. That way you can just focus your attention on the one or two that that requires a little bit more work and observations. So I like to do this. So I like to find general observations, and then my general observations are centered around a couple of things here. I think one of our restrictions is that we don't know the exact slope values, right? We don't know whether, is that a slope 10? Is that a slope 8? We really are kind of restricted in the sense that we don't know the exact values, right? We generally have an idea, okay, that's a really steep slope. That's probably closer to 6 than it is to 1/2. But a specific numeric value, we don't have that knowledge. So we're going to have to rely on these general observations. And general observations are categorized under 4 things that I see. Okay, the 4 things that are easy to identify are where slope is 0, though that's easy to identify, right? That's just going to be a horizontal line. Wherever there's a slope undefined, that's easy to spot because we're just going to be looking for empty spaces. Positive slopes, that's easy to identify. We want to look for a cluster of positive slopes, and then if we can, we're going to look for a cluster of negative slopes. So if I can say, oh, everything in the first quadrant looks like they're positive slope, I can use those observations to quickly eliminate my wrong choices if I see any choices that are conflicting with my general knowledge of what I see. Okay, so I'm going to make observations based off of things that are easy to identify. Slope 0, undefined slope, positive slope, and negative slope. All right, so here are my observations here. First is slope 0. I do see slope 0, but only along this line, right? I'm only seeing a slope 0 here. Everything else, I don't see any slope 0. So I see slope 0 when x is equal to 0. So that's one observation I can make. Slope undefined, I don't see any gaping regions where there's completely empty spaces, right? So I don't see any slope undefined. So that's an observation I can make. That means if something I see is creating a slope undefined, then I can eliminate that choice, right? So no slope undefined that I see. Third observation is positive slopes, mostly positive slopes, right? I do see something that looks like a vertical line, but we know vertical lines doesn't exist, right? Vertical lines should be slope undefined, and that should be empty. So if you see almost a vertical line, that means it's a very steep slope. But these are all positive slopes, right? Outside of x equals 0, it's mostly positive slopes. That's the third observation that I can make. So if anything is giving me a negative slope, I can pretty much eliminate that, right? We see that's not a property of this slope field. So it's mostly all positive slopes everywhere I look. Which means that my fourth observation is I don't see any negative slopes. And now what I'm going to do is I'm going to be looking at each answer choice, looking for ways for me to eliminate it, right? If I can find an exception to these properties, any of these properties, I know it can't be the right one and I have to eliminate it. So an easy way for me to target is, all right, negative slopes, right? I should not be able to get any negative slopes out of any of these differential equations. So if I can convince myself that there is a situation out there, a scenario out there that gives me even one negative slope, I can just eliminate it because that's a quick way for me. This is such a nice big observation. It will help me eliminate a lot of wrong choices quickly. So x cubed, can I think of a scenario where I'm going to be able to get a negative value? And basically, what any second and third quadrant is going to force that to be a negative, right? So if I have, let's say, -1, -1. Okay. I see a positive slope there. Doesn't take a y value, so it can take an x value. If I put -1 in for x, I get -1 cubed, which is negative, and we instantly tell that is conflicting with what we see in front of us. So this option is definitely not right. Okay, second option here. Can I force a negative out of any situation? And here we see x is being squared. So it looks like I'm not able to get any negatives out of this, right? If I put a -1 or 2, any negative number is positive, any positive number is positive. So that is matching pretty well. Mostly positive slopes. If I plug 0 in for x, I'm actually getting 0, so that matches up as well. And also no slope undefined. I'm not getting any denominator variable that's causing that to be undefined. So looks like this is a pretty good candidate for our answer choice. But just for practice purposes, we're going to keep going and see if we can eliminate the rest of these. All right, 2x plus y. Can I force a negative out of it so I can eliminate it? Well, anything in the negative third quadrant, right? Well, even second quadrant, right? Can you think of an ordered pair that will give me negative?
-1, 1.
Yep, -1, 1. Anything that, so if I test this out, -2 plus 1, that's negative. Okay. So that's the way I like to approach these problems. I'm looking for ways to eliminate. Rather than looking for the right answer, I'm looking for the wrong answers to make my choices easier at the end. I find that to be a faster strategy. All right, for D, what do you guys notice here? Why is this a wrong choice?
Everything at the origin would be 0.
Yeah, this, I'm seeing something undefined, right? And we already know that we don't see anything undefined, so that's conflicting. So y equals 0 should be undefined. I should see a whole bunch of empty spaces here, but these are all slope segments, so this is out. And the natural log of x can only take a positive value for natural log. So if I try putting in -1, I should be getting undefined everywhere here, but I don't see that's the case at all. So now usually we're going to see tomorrow that our answer choices is not going to be quite as easy as just eliminating everything just by looking at general observations. But you can tell that just by making observations, we should be able to eliminate most, if not all. And if you're down to 2 choices, then you can look at more specific order pairs to help you identify differences and eliminate them. So those are the more difficult ones where not everything cancels out, but general observations should at least get you 3, if not more, eliminated. So we can tell that 3x² is the only one standing. This is the only correct choice. Okay. Now there's another aspect to this that I want us to be able to do, is the fact that, let's look at the second statement. It says sketch a solution that passes through the indicated point. So we see a point highlighted here. Now what we're going to do is we're going to follow the path of this graph So this, imagine there's like a current, and we're just kind of following along the current, and we're just going to kind of follow wherever this current takes us. And then same thing here, right? If we just follow the current above, we're just gonna kind of follow the flow of the graph. And what I want to show you is that if we solve this differential equation, then that equation is going to match with what we know about the shape of this graph. Okay, so the solution is going to match with the shape of the graph, but the derivative equation is going to match with the microscopic, at the micro level, these each individual slope segments. Okay, so I want to show you what I mean by that. We're going to solve this differential equation. So we're going to extend this problem a little bit, and we're going to take the time to solve this differential equation and see how the solution is going to give us some knowledge about what we see in front of us. So dy dx equals 3x squared. I'm going to set it up for cross multiplying. So just like how we did last Wednesday, we're able to cross multiply, separate the variables, and then take the antiderivative. So I'm going to get the fractions out of the way here. So cross multiply. Okay, we take the antiderivative. Oh, first thing I notice is my x's and y's are nicely separated. Y is on the left, x is on the right. I've left the left side as minimal, as bare as possible. There's nothing I can do to move anything over. And that one just helps me see what needs to happen there. Okay. Antiderivative of 1. 1 will push me up from a constant to a derivative to a variable level, sorry. So 1 dy becomes y. And then 3x squared, go through power rule, we get 3x cubed over 3 plus c. Okay. The 3's cleans up nicely, cancels out. And we're left with y is equal to x cubed plus c. Now that plus c is just going to shift the graph vertically. But let's think about x cubed, right? What does x cubed look like? That's a cubic function. And cubic functions look like this. Okay. Do you see a resemblance? So this is the big idea that I want us to be able to take away, is the role of slope field. Slope field is going to match at the microscopic level with each of these segments, right? At the derivative level, this is going to provide information about each of these individual segments. But once we're at the solution level, then we're taking a step back and looking at how these slope segments are creating a pattern for us. And the pattern, or the flow of the graph that's created, is going to match with what we know about the general solution. Now imagine that plus c as plus 3 or plus 4 or minus 2 or minus 3, right? We can just pick any point on the graph and we can have it flow along the graph, and it doesn't matter where we start. We're all going to create kind of a general shape that are consistent with the cubic function. All right, so as long as we have a starting point, we can create a general equation that matches with whatever that c value could be. So now I want to be able to kind of go back and talk about the two statements that I skipped over. On the first page, I skipped over these two statements, but now we can have a better idea what this means. If we're at the differential equation level, which means that we're at the derivative level, we can use that to find individual slope segments, thereby is how we create that slope field. That's at the creation level. But then once we arrive at the solution, once we take the antiderivative, that solution should match with the shape, with the flow, with the general pattern of the graph. Okay, so the solution matches with the pattern, the derivative matches with the individual segments. Okay, so that's the big idea I want us to be able to take away. Okay, let's do one more. Let's do number 3. Okay. All right, just like before, I want to make my observations about slope 0, slope undefined, positive and negative slope. Where do I see a cluster of those information gathered? And one thing I want us to point out is about the x-axis. Okay. This is something that we're going to have to not rely on, because you see that there's an x-axis that is kind of making it difficult for us to know exactly what's going on there. Is this slope undefined, or is it slope 0 that just happens to be covered up by the x-axis? And I believe that it is purposely done this way so that students have to rely on other pieces of information. Okay, same thing happens on the AP exam. If you see x-axis with nothing on it, just know that it's one of two things, and we're not going to be able to rely on it because it could either be hiding a slope 0, or it could be slope undefined, and we're not just, but we don't know the difference. So we're going to rely on other information. We're not going to rely on the slope 0 because it's not very clear. Okay. But I can identify slope undefined, right? Slope undefined, I do see a place where there's a blank slate of nothing, and I see that is along the y-axis. So I see slope undefined. Let me separate these two problems. My observations is slope undefined at x equals 0, right? Along the y-axis, I'm getting a bunch of slope undefined. And what about clusters of positive and negative slope? Well, I see positive slope first and third quadrant. That's nice. I see an easy identifiable cluster of positive slopes here. So I see positive slopes in quadrant 1 and quadrant 3. And then I also see a cluster of negative slopes here, quadrant 2 and quadrant 4. And now I'm just going to look for ways for me to eliminate wrong choices. Right? All right, negative x, x minus 2. I'm looking for ways for me to eliminate it. What if something in the first quadrant, right? Maybe in the first quadrant, I can get a scenario where this gives me a negative number. And if it gives me a negative number, I know it conflicts, and I can eliminate that choice. So what if I test like 1, 1? Okay, if I put 1 in for x, I get 1 minus 2. Like this 1 is not used. So 1 minus 2 is negative. Negative conflicts. So I'm going to eliminate this choice. Okay. X cubed. Maybe I see third quadrant is positive. So if I choose a third quadrant, maybe I can force this to be a negative, and I can get that to go away as well. So if I test -1, -1, again, the y is not used, but -1 cubed is negative. We don't see any negative here, so that doesn't match. We can take that out. X minus y. What if I choose 1, 1 again? I get 1 minus 1, which is 0, and I don't see anything resembling 0 slope here. So that's not correct. All right, now y over x, when x equals 0, it's undefined, and that looks like it's consistent with that first statement. So maybe this is a choice that could be the correct one. Okay, let's look at these other ones here. Positive slopes. Now, anything in the first and third quadrant, the signs are going to be the same, right? Positive over a positive, negative over a negative. I should be able to get that property to be true. And then second and fourth quadrant, I'm getting negative slope because, let's see, this is negative followed by a positive, and this is order pair, positive followed by negative. And if one sign is positive and the other is negative, that's going to force a negative fraction, and that's consistent. And so I think this is our answer choice here for D. But let's look at E here just to confirm that this is also wrong. If I choose 0, for instance, right, E raised to a number is kind of hard to interpret, but E to the 0 is easy to interpret. So e to the 0 is equal to 1. So when y is 0, I should be getting 1. But when y is 0, I'm getting either slope 0 or undefined. That's not consistent with what I see here. So I know this is not correct either. So my answer choice is D. Okay, one last thing I want to do is to show that, look at the flow of this graph, right? The flow of this graph is kind of linear, right? If I choose any point, it looks like it's just getting me to some sort of a linear graph. There's no curve through any of these points. So if I were to solve this equation, I should be able to get some sort of a linear graph, some sort of a y equals mx plus b format. So let's confirm to see if that's true. I'm going to use the space for D here. I'm going to cross multiply, see if the solution matches with one of these line segments I'm able to create. Okay, cross multiply. I have all my denominators out of the way, but I can see that my variables are not separated. I want the y's on the left, x's on the right. So I can simply divide the y to the left and then divide the x to the right. The variables are nicely separated. If we want, we can push the dy and dx out in front to make it easier to see. And we can tell, right, these are rules that we recognize, 1 over u du, just natural log. I want to solve for y, so I want to get rid of the natural log. I can raise both sides, base e. So then I can eliminate this. I'm left with absolute value of y is equal to, and I'm going to separate the plus c and the exponent away from the rest of my other variables. So I'll say e to the natural log absolute value of x, right? A plus sign in the exponent region is going to turn into multiplication once we bring it down. And we know what happens with e to the c. E to the c is just a constant, so I'll have to replace this with just times c. And then I can also bring this down, right? E and natural log are also going to cancel out here. So I'm left with absolute value of y is equal to, this becomes absolute value of x. I can push the c in front as a coefficient. And we can drop the absolute value and let c absorb all the plus or minuses that comes along with it. And we're left with y equals cx. Now think about this. This is a linear equation, right? That c could be 2, so it could be y equals 2x, could be y equals negative 3x, could be y equals 1/2x, could be y equals 5x. Those are all different variations of these linear graphs with different slopes. All right, so all the variations that c could be are represented, and we have a solution that matches with the flow of the graph that we see in front of us. So again, a derivative differential equation is going to match at the individual slope segment level. And then the solution, once we find the antiderivative, is going to match with the overall shape and flow of the graph. Okay. So tomorrow, we're going to do a little bit more practice with matching, listing out properties and using those properties to eliminate the wrong choices. And then if we're down to 2 that we still can't eliminate, then we'll look at more detailed order pairs and see if we can eliminate it that way. So we'll practice that tomorrow. We're also going to do a little bit more practice with solving differential equations, finding a particular solution, tangent line equation, linear approximation, something that is more in line with maybe a test question format. And we'll practice also solving equations. And last thing I want to talk about is test recovery. So chapter 4 test recovery, right now I have it set on Friday. I set a Teams assignment. I sent a Teams assignment with details. I pushed it out to everyone. So if you want to recover your grade up to a 79, you can do the assignment that goes along with the Chapter 4 recovery. I'll have a help session tomorrow morning and 3:30. It'll be recorded. So if anyone wants me to go through test-like questions or help you make corrections on your test, and I will try to push out all the, I'll give the test details back to you so that you know what you missed. And if you want to attend this session, I can help you answer your questions. Okay. All right. Thanks, everyone. Hope you guys have a great day. See you tomorrow.
Have a nice day, Monsieur.
Thank you. Have a good day. Thanks, guys.